Here what we are going to do is now, so we are trying to see that what is the waveguides in the present context. What kind of generally why we see that these waveguides, and especially this is extension of the transmission line that more in the focus is I have to transfer the higher frequency signal throughout my one end to other end, either to in the board or in the kind of 3D. So if you take this, this is a 2D structures probably. You can see that this is kind of planar transmission line. This is called planar transmission line. Okay, and I'll come to that. This is both are no significance in terms of practical applications. Okay, so if you see that this kind of transmissions, where you see that this is strip line, this is a micro strip, just know this two the type in the planar transmissions. However, we don't see extensively in the syllabus, but it can be easily analyzed with whatever the concept which is learned in the transmission line. Okay, so that strip line is basically there are two plates in the top and bottom. There is here. Okay, there is a two metal plates that is called a ground plane, and inside there is one conductor. There is again metal. Usually it is a copper. It's placed no, exactly the middle of uh, the two metal plate. Okay, so basically what is this is the materials which is used. It is filled with the waveguides. Basically the ground in the top and bottom. I have in between the medium, which is a dielectric material, which can be typically what we use it. I'll tell you the what is the typical materials we will use that, and that is what a dielectric medium. And when it comes to the microstrip, I have only one ground, only one is there. Here two grounds are there, and typically if I take that the center conductor as it is will be retained in the strip line in the microstrip as it is. It will be the same in both cases. So here you can see the field lines. If you observe, there are the field lines. Basically, this is only the electric field lines, or you put it in the solid lines. Around that there is, you can see that the red colors, yellow color, and the green color. It is actually the magnetic line. This is our electrical lines. The solid lines are electrical. Okay, solid lines are electricals. Probably give me a second. I told no that there is some exam work. I'm getting a call regarding that. Give me a 2 minutes. I'll try to answer and come back. Okay, give me 2 minutes. Okay, excuse me for that, and give me a second. Yeah. So basically here, the electric field lines are solid lines, and these the magnetic field lines which is around my electric field lines. So if you can always imagine wherever this electric field is there, definitely there is a magnetic field will be there. Okay, H field will be there always. It's like a the pair, no, you can say a twin brother or twin sister, something like that. So now E is there, there will be H. There will H mean there will be E will be there. That is the physics nature of the electromagnetic signal. So that will be there. So and only the solid line is put up here. That is the electric field, and this is a 2D. The idea is to how it comes. The reason is to have a planar transmission line for a higher frequency is because of we need to get everything in the what you say the monolithic or kind of everything in one substrate. We want to amplifier, we want all the microwave components like inductors, capacitors, and filters, and phase shifters, and so on. So we want to make it in the like in the one shape, one substrate. Okay, so that is the reasons we cannot use these waveguides here basically. Actually, the waveguide concept came into existence of Second World War time during 1941. During the time where they needs to these concepts existed, you can read some one-page brief history is there. Around earlier, they've proved that mathematically the only the electromagnetic signals can propagate inside the tube. And they also mentioned if it is propagating inside the tube, so it has to meet certain criteria. What are the criteria is the frequency has to be such a way that it is above the cutoff frequency, and again there should be the dimension should be properly designed such a way that if I take this is a B, this is my A. So the B and A, the dimension is properly designed to see, all over that certain kind of frequency. So definitely this cutoff is related with the dimension. That is 100%. They derived it mathematically. Okay, and to make it realized practically it took some 30-40 years time because of the need to send a higher power and higher frequency signal, because for a radar antennas I need to basically use that higher frequency. The reason is the frequency is related with the antenna dimension. So in specific, if I fix the antenna, radar antennas onto my aircraft, for example, aircraft, or if you take the kind of this is my aircraft, if it into all the aircraft will have the antenna, okay, because without that there is no navigation. That is the basic thing, and again there is a base station should be there in the ground station to control this. That is also antenna. So this is fine. If it is a big I think it is not audible also, I guess. Probably I'm not on mute. Okay, I'm on mute. So probably I'll share it again. Okay. So when you see this, what I was trying to tell during the new time that so this is the practical device. I think you did not probably my voice is not audible. So I repeat that. Excuse me if you are already listening this. Okay. So basically, this is one of the practical the product, because I was thinking like introspectively thinking like Waveguide we are teaching, we are doing the 2-3 page derivation, and we are getting some results and doing some problems. So what actually we are happening in the market and the real time in the practical world. So basically these waveguides still it is used in the high power transmission and reception, either radar or the defense sector. It is still used. The waveguide is still necessary, and the waveguide is designed for particular frequency, 8 to 12, 8.2 to 12.4. This is WR90 is a standard for that frequency range. Typically, what we see it in the waveguide is how this dimension is matter to for designing this frequency. What is are the criteria to propagate the microwave signal, high frequency signal, basically. So that should be a cutoff. So cutoff frequency, when the operating frequency is more than cutoff frequency, my signal will start propagate inside the waveguides. Okay. So the basically the idea is, so we wants to know this concept. It doesn't know, it won't change that. And this mathematically is proved already and experimentally verified later. Okay. So the idea is to go to the waveguide is how to send this high frequency, high power signal. The more thing is double quote is high power. I can send high power signal in the planar transmission also, that what I am doing in the mobile phones. But still you remember, I cannot design it 8 to 12 gigahertz in the mobile phone. Okay, there is still a lot of challenges basically. If you take a 2G, 3G, still we are operating in 4 gigahertz, 4, 2, 4, 3, 4, 5 gigahertz. So I can show that probably there are more than these frequencies out there, probably. Okay, just I don't know whether I can show that. So it is a little slow, but just whenever you are studying, no, just keep these point also in mind. Basically, no, we are not reading which is not practically applicable. No, should not be think in that perspective. So that is one of the things I just want to tell you. So these are the many microwave components which is used in practice, and we are talking about in the waveguides. Okay, this is one of the companies, key companies. They are selling these products. So I am going about the flexible waveguides. Initially, it is kind of rigids. You can see it here. It's kind of rigids. Now they can bend it. Actually, the coupler is there, and there are the alternators, detectors. Okay, there are many components. So you can see it in the lab, which we are using it, and we have a planar antennas, patched antenna, that also available. So you can see that there is each waveguide is numbered differently, WR22, WR28, 34. So what is that basically? So when you see this, the lower the number, higher the frequency. Let us, I've shown that WR90, you just go to WR22. Okay, just I will click this here. So you can see the frequency is typically 32 to 50 J. No, I can give it in a paper. No mic planar transmission patch or whatever say that mobile phone. As of present technology, they can either transmit the power, but they cannot do any design. Basically, they cannot make any easily amplifier. They cannot make easily very high frequency circuits. Okay, that is a limitation in the planar transmission, because the planar transmission cannot handle more power, because I've shown that the two picture of strip line and microstrip. So that cannot, the dielectric will become more lossy. That cannot handle more power. Okay, but these pipe kind of structure can handle more power. That is the double quote I wants to tell you. So the main key significance of waveguide is it can handle more power. Okay, and still we are not into this range to design high frequency RF circuits. Maybe they are proposing terahertz oscillator, terahertz LNA, terahertz PLL, but integrating them and proper matching, impedance matching them, and making the still lot of difficulties are there. Still remember what we are using in the mobile phone, 4G or 3G, still not exceeded 5 gigahertz. Okay, still we are not gone into even more than 6 gigahertz. We have not gone. Okay, so that is a limitation there, but we have a compactness there. There is advantage here, advantage there also. So wherever it is necessary, we will pick that and we will use it. And when you see that here, probably this is my WR22. When I go with the higher number, my frequency, you can see that closely. When I are going for a higher numbers, the dimension is getting larger and larger. Maybe it is showing less here in this picture, but you can see that comparatively this dimension A and B, WR90 dimension is little bigger. So the dimension is playing one of the key roles for operating frequency. Okay, that practically seeing I can relate. Okay, these components. Okay, just seeing that inside, what is the waveguide inside, I can see that it is a rectangular structures. When you look this picture, you can see, this picture, and look this picture. Okay, this picture. Okay, so I think it is probably not very clear, but I'll zoom it and try to so this is WR22. You can see this, the dimension of it. WR22, you can see it's WR90. Why I'm saying WR90 is, I could have taken other numbers, because this is more closely what you are using in the lab, 8 to 12 gigahertz. This is X band waveguides. WR90 is X band, 8 to 12 gigahertz. That's what I'm going using in the lab. So that's the reason I've taken this waveguide. And you can see the dimension is little large compared to that. Okay, dimension is playing the role for operating frequency. So that's what a brief thing about the waveguides. This is why we need to have a uh, we need to look into these waveguides and start understanding some of the concepts. Okay, so here this is my 2D, this is my 3D, and comparatively this, which is better, stripline and microstrip. Okay, I give a 1 point of it. Still it may not be totally in the syllabus, but I can get just to give a comparison between these two, stripline and microstrip. I have a two kind of options for a planar waveguide, and which one I choose. So stripline came little earlier, microstrips came little later. The stripline is the thing is, it is giving effective protection. You can see that the field lines is contained inside, so there won't be the minimal chance of interference with the, there is a very less EMI interference. Okay, so electromagnetic interference is very less. So that is also critical part when I am designing the compact system, because when I have that amplifier, I may immediately have that filter, I may immediately have that mixer or a power amplifier, okay, or phase shifter. Okay, the interference should be very minimal. Even though there is encapsulations and their protective coating, there will be EMI interference is one of the key, or electrostatic discharge. So these are the secondary effect when you are going for a higher frequency. This will become a more predominant. So I have to take a proper care of the isolation of my fields. So this is striplines will give a better compared to the microstrip, because the microstrip there is no another ground, there is no another plate to protect it. Okay, so and the fields are typically here all are TM lines. There is an electric field and magnetic field. It is as similar like a two wire line. You have a transfer electric field is perpendicular, and also the magnetic field. This is a parallel. Okay, so this is as same as TM lines in the two wires. Here is not exactly TM, it is a quasi TM. It's called a quasi TM. Okay, here it is not typically, it will have a electric field perpendicular. It is not like it will. The reason is this is a dielectric medium. And one more thing is, where is the substrate? Where is the electrical medium? Here the electrical medium will be there everywhere throughout this, inside the conductor, between this conductor, where it will be here. I have to have this ground plane. Up top of it, I'll have the dielectric medium. Okay, So this will be actually, it's the air medium, this is the air surface, this is my dielectric epsilon, this is everything is epsilon. So the fields are contained here, but fields are here only contained partially, it is there actually leaky, and here there is inside the medium also substrate also there is, I have a field. Okay, this is called a quasi TM. I have interference there. And what is a, okay, if it is, this is good, why we are going this? The reason is, when it comes to the, what is say that, I could not find the exact word, during the VLSI applications we use that word. Basically we had want to have that, what we say is integration of all the components. As like a fabrication goes, it has to be like a kind of, like a coating, making a coating in the walls. No, if you have a painting we are doing in the wall, it should be done one layer, above two layer, above three layer. It is something like a kind of, no, one stacked. No, all the fabrication is stacked. That is what we do the p-type, and we do the insulation, we do the n-type, so that way we do the chips, right? So similarly, if you look this, the fabrication point of view, what I have to do is, first I have to have a ground plane, and inside, no, I have to put it inside strip line. So I have to think about some lithography techniques. Okay, I put this dielectric medium here first, and leave this space and do the metal deposition. Again make this again dielectric medium, and put it again, I put the ground plane. It becomes again one more steps. But if you take it here, it is more like a fabrication friendly. It is as no, as similar like a PCP design. We call as this RF PCP design. So what I have a substrate, just put on layer. No, the substrate, one thing is difference in the RF PCP to normal PCP is, in the normal PCP I have only the plastic substrate, which is what normally use the plastic. Okay, there nowadays they are trying with the, what you say, the flexible substrate. I think you have seen that, maybe in the mobile phone and the laptop, when you give it for a service, there is a flexible cables, no, the kind of cables which is connected to nowadays displays. So like that they are now making the PCPs also, flexible PCPs. Okay, this becomes more compact, and the display screens of laptop will be very compact. So that is the reason they are using a flexible connectors mainly made in China. And this is a substrate again made in China. But here what is that, normal PCP will have only the plastic. But in RF, if you reverse this, the PCP, the whole thing is, I coated with the metal. The bottom is metal. Okay, so I need another conductors to propagate. Like I need one conductor to propagate EM signal. Okay, so still it is needed two conductors, but here I have a three conductors. So here I can just make that one metal and substrate, and I'll just put the layers like however I want. I need, if I want, in case, let us take, there are, I'll show that inductor I want, I just put inductor here, and the out of, I can get it here and use that capacitor, some section stub matching, I'll use it. Just put all the thing. If you want antennas, kind of parabolic, I'll put the parabolic. It's something become an art, just to put everything in a different shapes, so you will get a nice RF PCP design picture. Okay, so you can Google, and a lot of pictures RF PCP design pictures are available. So there are a lot of even band pass filters. It will look like a comb structures. You will get a lot of pictures. I tried to download something, probably I don't know whether I have. If I have, I'll just show that. Yesterday I was thinking this, probably how I can relate this, some of the things which is needed to see that how effectively we can actually use that for our concepts. Yeah, this is one thing. You can just have a look. You can see that the beneath there is a, what you say, the RF PCP. This is as typically IC designs. No, this is a typically IC designs. But when it is connected to the PCP, this is a PCP, and this is my. I think you can see my, probably use that. Okay, I don't. Yeah. So this is my normal. I'll take another color. Okay, this is my normal IC design, and this is my, it comes to RF. PCP, and you can see that a lot of connectors are connected onto that again. So it is look like a normal PCP. So that is what advantage of microstrip. These all now presently we are using microstrip. Even though it is leaky, we are able to minimize that effect by choosing using that simulation CAD tools. We are trying to minimize the thickness of the substrate. We are trying to minimize that you choosing a right dielectric medium. We are trying to minimize it. Okay, that is what is the more things we are moving around microstrips. So that is the reason it is more so popular than the strip lines. Okay, so that what I want to discuss about this, the basic concepts of the waveguides and strip lines. And if you have any questions, you ask me. Probably another 10 minutes is there. Probably I'll take some questions, or else I'll just probably I'll start with some of concept related to the kind of the equations which we are seeing basically. Okay, so the point is the derivations. I'll try to do that, or else the notes, the derivations are there. My idea is to to make it understand. Probably I can show that what is the TE and what is the TM mode. Okay, I just if I remember that. Probably I'll show that. I think not everything, at least the minimal thing, and all the equations or the things can be derived and substituted and got composers. Maybe there are steps are missed, but still you can easily work out. Maybe there is one link I did not give it in the notes, but once you start the general equations till you get T or T Ez or magnetic equations, you can straightly can follow it as from the textbook. I've just added some of the intermediate steps, probably that you can refer it. So the derivation has to be kind of practice kind of thing. Okay, it need not be conceptually there is the things to be told. I have told what are the things we need to look into it when when we want to see the practical aspects. So I just want to highlight something whichever I told. Basically here there's a two wire lines. I have a magnetic fields around the coil and electric fields between these. This is what even planar transmission line. We have these two kind basically. There are one more type coplanar waveguides. Maybe that is also planar structures. I will tell you whenever it is relevant. When I'll tell you that is also one kind of planar transmission. Okay, that is for both any planar transmission we needed two conductors. But when you look at PCP design, we may wonder only one lines. But in the back of the PCP, another lines are there. Okay, there is a two lines is record for it electromagnetic signal to propagate. But waveguide is exception. There is only single conductor will be there. Okay, there is a question also you might have got probably there is a quiz questions. Now why the TM modes only exist in the two conductors, not in the single conductor? That is one thing. Or other way asking a problem is why the TM mode does not exist in the waveguide. Okay, similar questions. Okay, that will come to that. So TM modes record two conductors to propagate. This mathematically also is proved, like you needed two conductors to propagate TM lines. So if you look that okay, that is okay, then waveguides if cannot propagate TM modes, then what is the solutions? Then you can go either for electric or magnetic, transfer electric mode or transfer magnetic mode. So basically, so what is the transfer electric is the electric field is transverse, that is a perpendicular to the direction, and the magnetic field is this is a red color, that is actually the kind of parallel to the propagations, but the names the nomenclature is we always look for a which is transverse. Transverse is no, there is a two kind of the waves behavior. If you remember in the physics classes, there's a transfer wave is something like you take a stadium of people sitting. Okay, all the people, let us take football stadiums who are sitting in front. Okay, nowadays there is no people around the football matches because COVID. Okay, only the chairs and coaches and players are there. Okay, so anyway, if the normal situation, if the people are sitting, what is the transfer modes? The people, you assume that all are jumping up and down the sheet. That is what we call is transverse. Okay, the electric field like a jumping on the direction. Okay, it is not moving front and back. You just imagine they are jumping in the chair. That is my transverse. What is the longitudinal mode? If the wave is propagating in this direction, it's like a sea wave or fluid dynamics. Okay, that actually the heat is transferring like this longitudinal mode. So that is what we call longitudinal. That is propagating on this, but transfer is just jumping in the same position. It's not moving actually. But when you see that, I think if you remember big matches, football matches, the people show the flag. They'll start the flag in one end. They will be in the seat only. Just they don't move it, but they will just raise this hand or flag or their hand, uh, and it will like look like a wave actually. They will start. This person will just move up. The other person will little move little higher up. This person will move. So when you look that from the distance, it like there is a wave is there actually. I think some of you can relate that. It's just jumping like, but the timing is such a way that it's look like a wave basically. The wave all around the stadium, the nice the pictures you can see, either they will use the flag or they will just move and just stand and uh, sit such a way that it is the wave is around the stadium. Okay, that is the transverse. Okay, so that transverse electric is something like electric field is not moving, it is jumping in the same place. Again, it's jumping after some time. It is like a sitting in the different seats, right? This is transfer electric. And what is that magnetic is, which is I told it's a twin brothers. If electric is there, magnetic definitely will be there. Okay, there is a magnetic field now, should be as per the nature. The magnetic field is perpendicular. This is electric field, this is my magnetic field, that is perpendicular to each other. Okay, so why it's called transfer means because the electric field is transfer. Here the same thing is the magnetic field is transfer. If you look the magnetic field, it is not moving, just in this place it is rotating. This place it is rotating, that is a transfer magnetic. So electric field will be perpendicular, that is a longitudinal, that is it is on the direction. So the direction normally we will take it in the textbook is that even transmission line we have taken this is the z-axis. So if it is this is the z-axis, I can write this probably you can see it in the textbook. This is, if it is a z-axis, this is my x. I think this is my y. If I am not wrong, no, this is my x. This is my y. Oh, that is correct. You check that axis. Probably this is my x, this is my y. Okay. However, this is, I can take any axis, any number, but if you follow the textbook, it will be standard textbook. It will be even better. Okay. So come to the derivation parts. I have that this is what it will propagate the different modes. And one more thing is each T or TM there will be a different mode. The mode is actually look like this. There is, we have a half wave, this full cycle or 1.5 cycle. Okay, so these are the different waveguides. This there also in the lab. Okay, that this is a kind of derivation I used it. Probably you can, these are lengthy derivations, may not be necessary. You can just go to the Bowser and you can take it. The Bowser textbook, we'll get a TM general solutions, right? So that solutions I'm going to substitute. I'll just show the condition for T or TM. Okay, probably here itself, the first slide itself, there is a condition has to be met. This is what the important thing is. Okay, maybe in the textbook equations I would have followed this different textbook, but Bowser is quite good enough. So these condition is the important thing. So if he wants to take it from the general solution to the TE or TM mode, in exam either they will ask TE or TM. So if what is the transfer electric is, from if you look at the picture, the electric field is perpendicular. So I'll just erase everything. Okay, the electric field is here in this direction. So there is no any components moving on the direction. Okay, it's jumping, it is not moving. So in that say, because that case, I don't have any EZ. There no electric field on Z direction. So transfer electric means EZ equal to 0. So transfer magnetic means the magnetic field are jumping, so it is not moving. So it is HZ. So HZ equal to 0. So these condition is the very first important things you have to assume and before starting the derivation. Okay, the derivation is given probably you can look the picture. I just try to miss, there is one link is missed from the Maxwell equations to general solution. Probably the last class I some substitution I've done wrong. Probably I could not tell you that time probably. So I what I will do is I'll try to record or try to put it as a notes. So instead of taking a time for a derivations, and you can have a look on how to get this. I'm just following the Boser textbook and all the derivations from that. So only thing is how to take those equations and applying the problems is more important. I'll focus on that problems point of view. Derivation, I suggest you to uh, look the notes, look the textbook, and start substituting here and there, and definitely will be understanding it. The same kind of concepts we are using for deriving it, and we will with that problems, with that small note in the derivations, we will move into the S parameters. Okay, I'll try to share the notes. So with that, I'll stop this session. If you have any questions, you can put it me in the chat or put it me in the mail. I will try to answer it. Okay, so with that, I'll stop. Then take care. See you then in the next class. Okay.